Hello everyone and welcome to another video. Today I'd like to talk about Euler angles. Euler angles are three angles that were developed and introduced by the very famous mathematician Leonhard Euler in the 1700s, and we're going to see that they help play a very important role in describing the orientation of an object in space. Now, since I'm an aerospace engineer, the examples I typically like to look at involve aircraft. So why don't we go ahead and let's take this G.I. Joe toy aircraft as an example. So what I'd like to do is I'd like to be able to describe the orientation of this aircraft in space. So the first thing I need to talk about is orientation with respect to what? So we need to define a reference coordinate frame, and I think that's pretty easy to do. Why don't we take some virtual point, maybe right here. I'll call this the origin where my fist is, and in my case, north is actually pointing directly that direction. East is coming out of the page directly toward the camera, and then a right-handed coordinate system is going to make the z-axis be the down axis, which is obviously down toward the floor. So that gives us the north, east, down with its x, y, z axes respectively. So let's call that our reference frame. Now, as I'm sure you know, you can attach another coordinate frame to, say, this aircraft. So this aircraft has a center of gravity. Let's call that the origin. Let's place that origin at the same origin as this northeast down frame. So for example, right here, something like that. Now, as you know, the x-axis for the body frame of the aircraft starts with its origin at the center of gravity, and then the x-axis comes out the nose, the y-axis comes out the right wingtip, and the z-axis makes a right-handed coordinate system which comes through the floorboard of the aircraft. Now, as you can see right here, we have a slight, I don't want to call it a problem because it actually is kind of interesting and makes it a challenge, but we see that the body frame is not aligned with the reference frame, the northeast down frame. So what we want to do is we want to be able to describe how are these two frames quote-unquote misaligned or different than one another, right? What is the orientation of the body frame with respect to this reference frame or the northeast down frame? Now, we're going to see that is exactly what Euler angles do. They help us describe these the differences in these two frames. So what we need to do is we need to jump over and start thinking about exactly what are the definition of these Euler angles, as well as develop some of the mathematics that might be necessary to operate on Euler angles and subsequent operations. So if that sounds like more fun than a clown on fire, why don't we jump over to the whiteboard and get started? Okay, so why don't we jump into it? So one thing that I'll mention right off the bat is the thing that makes Euler angles actually interesting is not only are they just three angles, but they are actually associated with an Euler rotation sequence. So let's write that down. Not only do we care about the angles, but we actually care about the Euler rotation sequence. What I mean by that is that there's a specific order of rotations that we need to perform. So the goal with the Euler angles and this Euler rotation sequence is I want to basically be able to develop a set of rotations to go or start in some reference frame. We're going to call this FV here. FV for the vehicle carried northeast down frame, the one that we were just talking about, okay? I want to be able to start in the vehicle carried northeast down frame, and I want to be able to end in FB, right, which was the vehicle carried body frame, okay? That's the whole goal of the Euler angles in this Euler rotation sequence, is to basically develop a rotation matrix that is going to take a vector expressed in FV to make it expressed in FB. The goal, the way that we're going to do this here is we're going to start in the northeast down frame. Okay, so again, maybe let's write this down. FV is the same thing as F northeast down. Okay, and what we're going to do is you're going to go through a series of three rotations which use two intermediate frames. So the first thing we're going to do in this Euler rotation sequence is we are going to use a right-handed rotation about the ZV axis, okay? Which is going to be the same thing as the Z. We're going to call this the one frame. We're going to see later that this is these intermediate frames that we're talking about. So the first intermediate frame we're going to call the one frame. We're going to go through this right-handed rotation about ZV through angle psi. Okay? And this goes and it gets us to go to F1. And again, bear with me. Some of this notation might not make a ton of sense right now, but it will in a second. I just want to write down the sequence, okay? So that's the first thing. We're going to rotate about the z-axis through angle psi to get to frame 1. Then, once we're at frame 1, we're going to do another right-handed rotation about, now we're going to go about the y-axis, and this is going to be the y1 axis, which is going to be the same thing as y2. These two axes are going to be aligned, and we're going to rotate now through angle theta, okay? And again, this is to go to F2, our second intermediate frame, okay? And then finally, the third and final step that we need to do is we need to take a right-handed rotation about the x2 frame, okay, which is going to be the same thing as the x body frame, right? The one that we're trying to end at, okay? And we're going to rotate through the angle phi. And then this is basically to go to finally F body, okay? So that's the general gist of it. We were going to start in the vehicle carried northeast down frame. We are then going to rotate through angle psi by rotating about the z-axis. That will get us to the 1 frame. Once we're at the 1 frame, we are going to then rotate about the y-axis through angle theta to get to the 2 frame. Then finally, we're going to go from the 2 frame by rotating about the x-axis through angle phi, okay? So this might be a good point to maybe pump the brakes a little bit. And if you're not familiar with all of this discussion on the rotation or rotation matrices or these frames, I would highly recommend taking a moment. Make sure you've watched our previous video where we discuss expressing vectors in different frames using rotation matrices, because we're about to jump into it and utilize those rotation matrices quite extensively, okay? So if you've done all that, I think we should be okay. So maybe let's draw a picture of this so we're all on the same page about what do these 3 rotations look like. So the first one, let's draw a picture for the sequence 1. Okay, so we said sequence 1 was basically rotating about z, right? The ZV, which is the same thing as the Z1 axis. So what I mean by that is, let's draw ourselves the northeast down frame. Okay, so I'm going to make north in this direction. Let's call this X of the vehicle northeast down frame. This is basically north. Okay, then east is this way. So here's the y-axis of the northeast down frame. Well, this is basically the east direction. And then down is into the page in this case, right? So here's Z of the vehicle carried northeast down frame, which we're also calling down. Okay, now the idea is I want to now rotate my aircraft or my body or whatever through some angle psi, which is rotated about the z-axis, right? So the z-axis is into the board, so a positive right-handed rotation of about the z-axis is going to yield me this 1 frame, which sort of looks like this. So here's my x of the 1 frame through angle psi, okay? And then similarly, you would have y of the 1 frame. And then here's where you can see that z of the 1 frame, they're the same thing, right? Because I'm rotating about the z-axis, the z of the northeast down frame is the same thing, it's the same axis as the z of the 1 frame, okay? So the idea is we're going to start in the vehicle northeast down frame. I'm going to rotate my aircraft so that it now is aligned with this 1 frame. So I'm going to, this is my horrible picture of an aircraft. Oh gosh, this is going to make this thing very... Let me clean some of this up so we can hopefully see this a little bit better. Okay, so here's my horrible picture of an aircraft. So something like that, you get that, right? Here's the wings, here's the empennage and the vertical horizontal stabilizer. Gosh, that's a horrible picture. Maybe let me get my prop here, and maybe this is an easier way to say it, right? So the vehicle starts aligned with the northeast down frame, and now I'm going to rotate it about the z-axis through angle psi to get to this 1 frame. Okay, so that's how these things are different. Okay, all right. So that's the picture that goes along with the first sequence. How about the second sequence? Okay, so sequence 2, right? This is a rotation about what do we say? The y-axis, right? About y1, which is the same thing as the y of the 2 frame, right? So that's sequence 2. Okay, so again, let's draw this picture. And I think it's probably easier to look at it from the side. So again, let's draw the origin here, okay? And now the one frame, let's just make this thing sort of aligned like such. Maybe let's try not to take up so much room. Might need that room in a second here. Okay, so here is the x-axis of the one frame. The y-axis of the one frame is coming out of the page. Okay, and then the z-axis of the one frame is obviously down. Okay, so there's our right-handed one frame. Now, if we look at this sequence here for rotation number 2, I'm going to rotate about the y1 axis, which is coming out of the board, right? So now, in this case, coming out of the board is the axis of rotation. So a positive right-handed angle theta is actually in this direction, right? So a positive is something like that. So here's the x, here's how the x-axis will rotate from the one frame up to the two frame through a positive angle, positive theta. Maybe we should have put the positive sign on this just to make sure we're on the same page, okay? So again, that's going to obviously make the z-axis also rotate. Here's Z2. And you can see why, again, why the Y1 frame and the Y2 frame are axes are the exact same, right? Because we're both rotating about the Y axis as the axis of rotation, so they stay the same. Both of them are still coming out of the page. So now, if I wanted to draw our aircraft, I guess this is now our side view of the aircraft. Here's the cockpit. Oh boy, and again, I apologize. I am not the best artiste. So here's maybe our wing, here's the cockpit, right? So again, maybe the better way to do it is look at our prop. So we did a couple of things. First of all, we were aligned with the northeast down frame. We rotated about the z-axis through angle psi. That got us to this orientation, okay? And now what we're gonna do is we're gonna rotate about the common y-axis, which is coming out of the page, up through angle theta to get this thing pitched up slightly, okay? Great. So now the last thing that we need to do is rotation sequence number 3, and let's see if we can shove all this in the boards in one place. So sequence 3, this was a rotation about the x-axis, right? The x2, which we said is going to be the x2, which is the same thing as x body. Okay, so the picture that goes along with this is, I think maybe it's easiest if we look at this kind of from the back. Okay, so if we look at it from the back, what we've got here is, let's draw the Y2 frame to start with. So here's Y2 is in this direction. Okay, X2 is going into the board. So here's X2 going into the board. And then finally, that means right-handed coordinate frame, Z2 is down like such. Okay, now reading this, we said that we're going to rotate about the x2 axis. So again, x is going into the board, so a positive angle phi is going to look something like this. It's going to rotate this picture to make this look like the y body. So here's our positive angle phi. All right? And that'll also kick over the z-axis, so now here's z body. And again, we have the same thing. The x2 and the x body axes stay the same because that's the axis of rotation. So now, again, if we draw the aircraft, we're looking at it from the back. So gosh, how am I going to draw this? So here's one of the wings. Here's another one of the wings. And then I guess we should probably see the tail like this. Here's the T-tail configuration, and maybe the cockpit is over here. So again, my horrible picture is, we're looking at the back of the aircraft. I don't know if you can see that too well in the camera, but you're looking at the back of the aircraft, and now we're going to rotate that way, right? The right wingtip goes down for a positive phi. Okay, that gets us to the body axis. So if we put all of this together, maybe I'll come over here where you can see this a little bit better. What we're talking about now is, let's point it, let's go back to our example, I guess, where we're going to pretend north is that direction, okay? So what these three Euler angles are they're defined relative to these intermediate frames. So this first angle psi, that angle psi is how much do we rotate about the z-axis. So we're going to rotate this aircraft through an angle psi. So in that case, that looked about like psi of 45 degrees or something like that to me. So now we're not pointing north, we're kind of pointing northeast, actually exactly northeast in this case. Okay, now we're going to go to this rotate through an angle theta. So if theta was I don't know, 20 degrees, all I would do is I would tip this up 20 degrees from where we are now. Okay, that's 20 degrees, and now we can use the angle phi, which is sort of our quote-unquote bank angle. Again, I put this in quotes. You're going to see why I'm putting this in quotes a little bit later when I discuss. We got to be a little bit careful. But our bank angle now is, let's make something up. Again, 45 degrees or something like that. So, or tell you what, let's make it negative 45 just to be interesting. So negative 45 degrees would mean from this frame, right now we're sitting in the 2 frame, correct? Now I want to rotate from the 2 frame through negative 45 degrees. So that's actually this direction, right? A left-handed rotation. So something like this. So now this aircraft right now, or this body frame, is oriented associated with an Euler angle of psi of 45 degrees, theta of, what do we say, 20 degrees, and phi of negative 45 degrees, okay? So that's what these Euler angles are. Again, I apologize if that was not entirely clear for me, like drawing this out on the board or playing with toys. Why don't we jump over to Matlab? I've got an animation to show you how these Euler angles and all these intermediate frames play together. So let's jump over to Matlab real quick and let's see if we can visualize this a little bit better.
All right, so to get a little bit more practice, let's use slightly different numbers. Let's use a phi, theta, and psi of positive 70, positive 130, and positive 25 degrees for the yaw, pitch, and bank angle, respectively. So the first thing that we want to do is let's draw the starting frame, or our vehicle carried northeast down frame, which we were calling FV. So again, the x-axis is pointing directly north, the y-axis is pointing directly east, and the z-axis is pointing directly down. So the first thing we want to do in our Euler rotation sequence is, starting from this V frame, we want to rotate about the z-axis through the yaw angle of psi equals positive 70 degrees. So let me just draw the one frame in green. So the green frame is F1, and as we can see, if psi is equal to 0, as you can see in the figure title, there's no difference between the one frame and the V frame. However, as we start increasing the psi Euler angle, we see that we offset the one frame from the V frame by rotating through the common z-axis. And now we reach the one frame as drawn here in green. So the next thing we want to do is we are now going to pitch through the y-axis to go from the one frame to the 2 frame. So that's what I'm drawing here in orange. So orange here is the 2 frame, and again, as you can see, if theta is equal 0, if the pitch angle is 0, there's no difference between the 2 frame and the 1 frame. So there's no difference between the orange frame and the green frame. Okay. However, as theta starts increasing, what we're going to do is we are going to start rotating about the common y-axis, right? So that here is this axis right here. So this is the y1 axis, which should be the same thing as the y2 axis. So let me go ahead and let the animation run, and what we're going to do is, as the pitch angle increases, you see that the 2 frame just starts being offset from the 1 frame, but their y-axes stay the same, right? That's the axis of rotation. So the third and final sequence in our Euler rotation system is to use the bank angle of positive 25 degrees. So again, let me just draw that here in blue. So blue is our final body frame, right? And right now, if the bank angle is 0, again, as denoted here in the title, the body frame in blue is the same thing as the 2 frame, which is drawn back here in orange. Now, what we have to do is now we are going to rotate about the x-axis, right? The x-body axis, which is the same thing as the x2 axis. And that should be this one right here. Okay? So again, let's let the animation run, and you can see that if we bank through positive 25 degrees, the body axis in blue becomes offset from the 2 frame, which is in orange. Okay? And now we finally arrive at the body axis in blue, which is now relative and offset from the vehicle carried northeast down frame here in red. And tell you what, just to make that clear, I will draw them here without any of the intermediate frames. So again, all we were trying to do here is describe how this body frame in blue is different or oriented slightly offset from the reference frame, which we drew here in red. And we saw that the way we got there was by going through this Euler rotation sequence of utilizing those two intermediate frames of F1 and F2. Okay, and actually, tell you what, let me just rerun this entire animation without stopping, and maybe we'll plot one of them on top of each other and let it all run smoothly in one shot, so it might make a little bit more sense. So let me go ahead and close all these figures. And again, we can just refresh our memories, and we said that we're going through a yaw angle of 70 degrees first, about the z-axis. Then we're going to pitch through 130 degrees by rotating about the resulting y-axis. And then we are going to bank through positive 25 degrees through that subsequent resulting x-axis, excuse me. So if I just run that whole script one at a time, we see here's the z rotation, and then here's the y rotation, and now here's the x rotation. And we finally end up at our body frame relative to the V frame. So for giggles, I'm just going to run this one more time so you can see how those three sequences interact with one another. And we see that they are subsequent sequences. One follows the other. Okay? All right, so with that being said, I think it would now be helpful, now that we can visualize and understand how we go from the vehicle carrying northeast down frame to the body frame. Let's jump back over to the whiteboard and look exactly at what are the rotation matrices and the equations that we need to relate one another.
All right, so now that we saw how those Euler angles are defined, I think we can start writing down what are the equations that relate a vector expressed in the vehicle carrying northeast down frame to a vector expressed in the body frame using these two intermediate frames. So as a quick disclaimer, we're going to be using some notation using rotation matrices and expressing vectors that we covered in one of our previous videos. So if you haven't watched this video, please make sure you watch this first, because we're going to be leveraging a lot of the tools we developed in that in the subsequent math. So to start with, I left up our Euler rotation sequence here on the board because we're going to want to use this and help us refer to the sequence, because we're going to see that the sequence is actually key. So the first thing let's do is let's tackle this first rotation here, which goes from the V frame to the 1 frame. So in other words, what I'm saying is, let's say that we've got a vector, right, expressed in the vehicle carrying northeast down frame, right? That's this one right here, right? And now what we're going to do is we're going to rotate about the z-axis through an angle psi. So all that is, right, is that's a rotation matrix from one frame to another about a z-axis through an angle psi. So all that is, right, is it's a rotation matrix from V to the 1 frame through the angle psi, right? And that is going to yield a vector, the same vector, but now expressed in the 1 frame, okay? So in this case, this rotation matrix that we said earlier in our other lecture, right, is we said that this C1V over psi, right, all this guy is a rotation matrix. I guess we're going to run out of room here. Let me just erase part of this picture so we can have enough room to draw the rotation matrix. Hopefully you've got the rest of that in your notes, right? This is just, again, it's a 3x3 rotation matrix about the z-axis. So we've got a 1 down here and then 0, 0, 0, 0. And then in these other intermediate entries, all this is, right, this is now just cosine psi, sine psi, minus sine psi, and then cosine psi, right? That's all that rotation matrix is. So there we go. We've taken care of this first rotation, okay? Now, let's myopically look at just this second sequence of our Euler rotation sequence, right? So just this second rotation right here. All this is if you look at this long enough, again, it's just a rotation from a starting frame to an ending frame by rotating about a common y-axis through an angle theta here. So in other words, what we're going to say is, let's say you have a vector expressed in the starting frame, which was just the 1 frame, right? And I want to rotate this using a rotation matrix which goes from the 1 frame to the 2 frame, right? It goes from the starting frame to the ending frame through an angle theta, right? So we're going to denote it like such. This. And that is going to give us this exact same vector, but now expressed in the 2 frame. And again, all this thing is, right, is this rotation matrix is, if we want to write this thing out, 2, 1, theta, right? It's again another 3 by 3 rotation matrix. Sorry, I'm gonna have to keep erasing my picture to get us a little bit more room. Okay. Again, it is a 3 by 3 rotation matrix. But all we're doing now is we're rotating about the common y-axis, so the 1's got to go here, and let's put out zeros everywhere else and other terms. And then to get the rotation, it's now just cosine theta, right? And then minus sine theta, cosine theta. Great! So that's taking care of this second sequence. Now, again, let's come down here to the third sequence, or the third rotation in our Euler rotation sequence, and just myopically stare at just this one. So that's over here. Again, if you look at this picture, again, all it is, it's a rotating from some starting frame to some ending frame by rotating about a common x-axis through the angle phi, okay? So again, we're saying I've got a vector now expressed in what the starting frame is, which is now in this case 2, and I'm going to rotate this guy from 2 to the ending frame, which is the body frame, right? To the body frame through an angle phi. Okay, and that's going to yield me a vector expressed in the ending frame, which is the body frame. And again, this rotation matrix, this C2 to B through the angle phi, it's nothing more than a 3 by 3 rotation matrix about a common x-axis. So the 1 goes here. And then these terms are going to be cosine phi, sine phi, and then minus sine phi, and then cosine phi. There we go, okay? So what we can now do is, I guess we can continue over here. Let's see if I can jam all of this into this small part. Can you actually see that on the board? Yeah, okay, good. So let's go ahead, and maybe I'll draw a line here. We'll start. What I want to do is, let's see if we can now get an expression which takes us from the starting frame, our original starting frame, which is the vehicle carrying northeast down frame, all the way to a vector expressed in the body frame, okay? So let's just start with this equation, right? It says UB is equal to CB2 of phi times U2, right? Okay? And, well, what is U2? Well, if you look here, here's an expression for U2. So let's just take this right here and substitute in for U2, right? So this now becomes CB2 of phi. And now I'm going to substitute my expression for U2, which is this one right here, right? It's C21 over theta times U1, right? Okay? Now, again, where's U1? Aha, here's an expression for U1 right here. So again, substitute this in for U1. And again, shucks, I'm running out of room. I hope this is going to fit. CB2, let me see if I can just try to draw this cleanly. C21 over theta. And our expression for U1 is going to be C1V over psi times UV. Perfect. And now, let's box this thing up, right? And maybe I can fit everything onto the board, okay? This here is our expression, which goes from the goes from the northeast down frame to the body frame, and the one single rotation matrix that's going to take care of that for us is actually the product of these 3 rotation matrices multiplied like such. So this whole thing, the thing I'm circling here in blue, right? We could alternatively write this in one compact form. Where can I do that? I want to keep this line up because, tell you what, let's erase some of this up here. Okay, let's erase this. I think we don't need the picture too much. We can leave the words up. Okay. All right, so what we end up with, our final expression here, is basically that you have a vector in the vehicle carrying northeast down frame. I want the vector expressed in the body frame. It is going to be some matrix, right? It's some rotation matrix which goes from V to B, right? And now this is a function of actually phi, theta, and psi. Okay, and what this matrix is, it's just this term in blue here. So here, this thing is one giant rotation matrix, CB, let's see, what do we call it? Phi, theta, psi, right? This thing is the product of these things all together, right? It's CB2 phi times C21 theta times C1V psi, all right? So, oh boy, I don't want to do this by hand because as you can see, it's 3 matrix multiplies with a bunch of cosine signs. Let's run over to Mathematica and have it calculate this. We'll just do this quickly just so we can see what exactly is this matrix, okay?
All right, so let's go ahead and define those intermediate rotation matrices. So let's do the first one. So this was going from the northeast down to the one frame through the angle psi. And again, we said that was a 3x3 rotation matrix where it looked something like that, right? So then we got cosine of psi, sine of psi, and then minus sine of psi, and then cosine of psi, right? Whoops, psi. Okay, that was the first rotation matrix, and then the second rotation matrix, actually, I've got this already copied here, so you don't have to watch me type it all in, but here, this is going from the 1 to the 2 frame over the angle theta, and finally, the third rotation matrix, which was going from the 2 to the body frame over the angle phi, was something like that. Okay, so now what we can do is we can go ahead and get the final rotation matrix. Well, I'll tell you what, let's shift enter and get those guys into Mathematica first. And now let's compute the final rotation matrix, right? We said this is going, whoops, I got it the wrong way. I got to make sure we get this right, BV, right? So this is going from the vehicle northeast down frame to the body frame. And we said this was as a function of phi, theta, and psi. Right? And this was going to actually be what? It's CB2 of phi. So that times C21 of theta times C1V of psi. There we go. So that's what this should be. So let's shift enter that guy. And now let's take a look at what this guy looks like. And as you can see, it's not pretty, but it's easily calculatable. So we can calculate it quite easily. So let's jump over to the board and ask ourselves, what does this thing do? What's it called? How can we use it? And things like that.
All right, I've tried to transcribe as best as I could the Mathematica output here to the board. I've used some abbreviations like C theta means cosine theta, and S phi means sine of phi, just to save ourselves some room. And again, I might have made some mistakes here, so trust what was on the Mathematica output, not necessarily what was put up here, but I just want to again point out that again this rotation matrix, it's just a 3x3 rotation matrix, and all of its entries are just a whole bunch of cosine and sines of the Euler angles. Okay, so this here is this rotation matrix which takes us from the vehicle carried northeast down frame to the body frame. Now the one thing that I might want to note here, we might want to discuss here, is if you think about this long enough, we might also want to add a slight bit of notation to this rotation matrix. So we might want to call this, V to B over again of phi, theta, psi, right? But the reason I've kept this up on the board for so long is because it's now relevant to our discussion in the sense that these Euler angles, psi, theta, and phi, they are referenced to a very specific sequence or ordering here of going about the z-axis, then the y-axis, then the x-axis. So we might want to say, put a superscript or something like that says this is like z, y, x, right? To denote that that's the sequence that this Euler angle rotation sequence is taken with, right? There's nothing that said we couldn't have gone x, y, z, or z, x, y, or right, some other arbitrary order. So it might help to add this notation here, right, so that you're very explicit about what are these Euler angles. Okay, so that's the first thing to note here. Is let's make a quick note, like N1, order matters, right? So this sequence of z, y, x is typically understood to be the standard version in the aerospace industry. So usually we will drop this notation. So if you don't see explicit notation about what the sequence of the Euler rotation angles are, understand it to be, at least in aerospace application, it is going to be z, y, x in this order, right? The other thing to also note, let's make a note N2. Okay, typically most people, again, while we're talking about aerospace conventions here, aerospace conventions, people are typically going to want to be talking about phi, theta, psi, kind of in that order. So I've written that here as the order of the input arguments of this Euler rotation sequence. Okay, now this is, I'll just maybe write that phi, theta, psi is typical reference order. So people, when you're putting together a state vector or things like that, typically it goes phi, theta, psi. Now, the reason I again call this out here is if you look at this, it's a little bit, it might go clang in your head because really you're actually rotating over psi, then theta, then phi. So your natural inclination might be to say, oh, I'll talk about things, if I give someone a sequence of 3 Euler angles, I'll give them psi, theta, phi, okay? You just have to be careful about what you're doing here because most people in aerospace are going to assume that if you give them three Euler angles, it's going to be bank, pitch, yaw, right? So in other words, if somebody gives you a vector or if you're reading this in code and you see something like, oh, your state vector is something like 30 degrees, 80 degrees, negative 20 degrees, right? You just have to be very explicit. Which one of these are these? Most likely this means this is phi, theta, and psi, right? So it means that you have a bank angle of 30, a pitch angle of 80, and a yaw angle of negative 20 degrees. Even though the actual ordering of how you execute those rotations is actually the other way around, right? You first yaw through negative 20, then you pitch through 80 degrees, and then you bank by positive 30 degrees. But as long as we're all consistent, we're all on the same page, I think everything should work out. So this is typically understood to be the rotation matrix which takes you from the northeast down to the body frame. The way you get there is you go through this ordering of you first go rotate about the z-axis, then the y-axis, then the x-axis. So again, you typically won't see this superscript notation, but just be cognizant of where you are doing this, okay? All right, so I cleaned up the board a little bit to get us some room. A couple more remarks about this matrix, this rotation matrix. This product of these 3 matrices, you'll also sometimes hear this referred to as the direction cosine matrix or DCM. And you can kind of see where it gets this name, right? It has something to do with telling you about directions, and as you can see, there's a lot of cosines and sines in it. So this is sometimes referred to as the DCM. One thing that we might want to make a quick note of here is this DCM isn't necessarily unique in the sense that you can have different sequences of Euler rotations that will get you to the same DCM and therefore get you to the same sort of orientation of the aircraft. So as a quick example, maybe let's come back to our aircraft toy here, right? And we said that, okay, typically, you know, here's your starting northeast down frame. Let's rotate this to some new body frame. Like, for example, what happens if we were to just do nothing but pitch through 180 degrees, okay? So the only Euler angle that we're going to have is, let's look at maybe case 1, where your phi is equal to 0, theta is equal to 180 degrees. I'll write this in radians. And then your bank angle is 0, right? So what that looks like is, okay, you start here and all you're going to do is pitch through 180 degrees. So you basically end up with the vehicle flat on its back pointing due south, right? Okay, so that's one way you could get to this orientation, but another sequence of Euler angles that could also get you there, right, is what if you were to say yaw through 180 degrees, whoops, 180 times pi over 180. You were then to do no pitch at all, but you then bank through 180 degrees again. Okay, so again, going through our Euler rotation sequence now for case 2, that is yaw through 180 degrees, which will get you pointing like this. Okay, pitch through 0 degrees and then bank through 180 degrees, a positive 180, and I got to make sure I get that right. So it's positive around the resulting x-axis. So you get like this, right? So again, we end up in the exact same orientation, right? Given two completely separate sequences of Euler angles. Both of these, if you plug these two into your DCM, both of those are going to result in a DCM which equals crud. I wrote it down so I wouldn't forget. You can plug it into Mathematica, but basically just jam those sequences into our DCM expression. I think you're going to get -1, 0, 0, 0, 1, 0, 0, 0, -1. Okay? So again, we got to be a little bit careful and just make a note here that these Euler angles are not unique here. Okay? So all this leads to a discussion here that Euler angles are not unique. Okay? This has some bearing on some of this discussion. You may have heard of gimbal lock or things like that. And actually, this sets the stage nicely for later on down the road when we want to talk about quaternions. If you don't care about that now, just forget about it. But just to tickle your fancy, we'll talk about this a little bit more later. But again, they're not unique. Now, unique, though, that kicks off another discussion. Even though the Euler angles are not unique, that might lead you to ask the question of, well, if they're not unique, does that mean this matrix is singular at some points? The answer to that is actually no. So tell you what, let's erase the board and let's take a look at that next. Okay, so the question now is this DCM, is it ever singular? The answer is actually no. We can actually do better. Not only is the matrix never singular, it's actually unitary, and we can show that, okay? So what we want to do now is let's show that DCM is unitary, right? Which basically is going to make it so the answer to this is basically no. It's never singular, okay? So the way that we can show that this thing is unitary, if you remember, the idea with a unitary matrix, right, is that you've got this matrix CVB. I'm gonna forget all these arguments now just to make our notation a little bit easier. What the idea with the unitary matrix is that if the inverse is equal to the transpose, basically, this implies this happens if and only if this thing is unitary. Right? That's the concept of unitary. That's why unitary matrices are so great. I don't need to take the full inverse. I just need to take the transpose of this. Okay? All right. So what we should do then is let's go ahead and check, is this actually true? So let's see. Can I compute what is CBV inverse? Okay? So, well, this thing, let's expand. What is CBV? We have it right here. CBV is the product of three other rotation matrices. So it's CB2 times C21 times C1V, right? Okay, inverse. Okay, if you remember the property of inverses, right, I can distribute this inverse through by just flipping the order of this. So I end up with C1V inverse times C21 inverse times CB2 inverse. Okay? So now the question is, what are all of these inverses here by themselves? So what we need to do is we need to have a quick side discussion, right, on what is C1V inverse, C21 inverse, and CB2 inverse. Now, we can actually show that all of these are going to be unitary. C21, CB2, transpose. So these guys as inverses are their transpose. So that happens because all of these guys are basically unitary. Okay? So again, let's check that, all right? Don't take my word for it. Let's just make sure that this is true, okay? So again, we need to back up and let's ask ourselves, are one of these individual rotation matrices, are they unitary, okay? So again, to do that, let's see, where can I go get some room? Let's come over here, okay? And let's go check that. So let's go ahead and compute what is, in order to check if one of these are unitary, let's start with just C1V, okay? So if this thing is unitary, then if I multiply it by its transpose, right, I should get the identity matrix, right? Because if that's true, that means this term right here is by definition the inverse of this term. Okay, and similarly, I need to check the other direction, right? C1V transpose times C1V. I better get the identity matrix there, right? If this happens, that means that this matrix is unitary, okay? So let's go ahead and do this. And I actually don't want to do this by hand. Let's go over to Mathematica and do this, because we see that each one of these are just very simple 3x3 matrices with a bunch of cosine and sines. Let's just take the matrix, multiply it by its transpose, and see if we can get it to, if that's actually the identity matrix.
All right, so here we are in Mathematica. So let's go ahead and check if C1V is unitary, right? So we said the way we're going to do this is we're going to go C1V of psi, and we're going to dot it with its transpose by basically, that's basically doing our matrix multiply. So this is basically checking here if C1V times its transpose, what does that equal to? So let's call this some temporary matrix, and then I guess we can look at this thing in matrix form. And, okay, well, that didn't exactly look like the identity matrix, but actually it does, right? If you look at this closer, what's cosine squared plus sine squared? Isn't that 1? And same thing, cosine squared plus sine squared, isn't that 1? So actually, if I ask Mathematica to simplify this thing, yes, we see that that is indeed the identity matrix. Now, let's also go ahead and do it for the opposite, which is just this transpose dotted with itself. And again, we get another big fat identity matrix. So yeah, we know that C1V, the rotation about the base rotation matrix about a z-axis is unitary. We can do the exact same thing for the rotation matrix about the y-axis, right? That was, what do we call this thing up here? Yeah, here we go. C12 of theta. So C12 of theta times this thing of theta, and then again we'll check like this, and again we should see that this is unitary. Whoopsie, what did I do here? Oh, sorry, nope, see, I messed that up. There we go. Okay, yep, yay, another bunch of unitary matrices. So we see that the rotation about the y-axis is unitary. And finally, just for completeness, let's make sure that a rotation about an x-axis is also unitary. So again, we'll do this guy, whoops, of phi, and we'll multiply it by itself transpose. And then we'll do the same thing down here. We'll go transpose of the x-axis rotation times itself. Should, again, yay, turn out to a whole bunch of identity matrices. So we see that these three matrices, these rotation matrices about the z, y, and x-axes, those are all unitary matrices.
All right, so we just showed that all three of these things are unitary matrices. So what we can do is up here, back to our discussion, is I don't need to take the full inverse. I can just go ahead and take the transpose, dotted with C21 transpose times CB2 transpose, right? That's the exact same thing. Let me erase down below so we get a little bit more room. Okay, so if those are true, okay, let me go ahead and rewrite this. Again, remember your rules with the transposes. I can pull the transpose out of this by, again, reversing the order of this. So we end up with CB2 times C21 times C1V, all this transpose here. And this here, that was just CBV, right? That's this entire thing in parentheses, and then I put the transpose out here. So we end up seeing that, again, this DCM, the full DCM, is unitary, right? So therefore, it is never singular, right? Which is actually pretty darn cool. So we see that this rotation matrix, even though it looks complicated, since it is made up of a product of three unitary basic rotation matrices, it itself is also unitary. So again, if you're implementing this in code anywhere or doing something like that, never ever waste time taking the inverse of this thing. Just take its transpose to get the inverse because it's unitary. The other thing that might be helpful to talk about while we're just staring at this is also note that sometimes you may want to recover the Euler angles if given the DCM. So sometimes you're given the direction cosine matrix, basically this guy, and you want the Euler angles phi, theta, and psi, right? So there's a couple of easy ways to do this. I think the easiest way to do this is if you look at, you know, for example, phi, or actually, no, tell you what, let's do theta. This is easy right here. If you look at this entry here, the 1, 3 entry of the DCM is basically negative sine theta. So really what you end up with is if we back solve that thing, you can basically say that theta is basically negative inverse sine of the 1, 3 element. Okay, so C13 is supposed to be the 1, 3 element of the DCM. Similarly, if you look at this, there's a couple of other relationships you could get by basically playing around with the 1, 1 and the 1, 2. And I think if you stare at this thing long enough, you can see that, okay, phi is basically going to be the atan 2 of the 2, 3 element and the 3, 3 element. So again, we got to be a little careful with the a tan 2, right? I'm assuming that this is the y component and then the x component of it. Okay, that's how I'm writing this a tan 2 argument. And finally, psi here is going to be a tan 2 of C12 and C11. Right? Okay, so this kind of information is going to be useful later when we study Poisson's kinematical equations, and we're going to see that we're going to maintain the entire DCM, and then anytime during the process or the simulation we may want to understand the Euler angles, well, we can just use these three equations to get those Euler angles. Now, we've been talking about how the Euler rotation sequence is made up of these three individual unique rotations. You may have heard, though, that it's possible to go from one frame to any other frame through a single rotation about some unique axis of rotation using just one single rotation. And that's definitely true, and I want to talk about how we get there, in particular how this relates to Rodrigues' rotation formula. So you may remember that we talked about this formula in one of our previous videos over here. So again, if you haven't seen this video, I would recommend taking a moment to stop and watch this video, because we're going to be using Rodrigues' rotation formula to investigate and derive what this axis of rotation that we're talking about is, that will take us from FV to FB in just one single rotation. Okay, so to do this, let's tell you what, let's first go ahead, and what I want to do is let's compute the eigenvalues of the overall rotation matrix CBV. Okay, so let's go actually and have Mathematica do that, because as you saw, this matrix is kind of ugly. So as you can probably imagine, the expression for its eigenvalues might be kind of ugly. So let's jump over to Mathematica and get the eigenvalues quickly.
All right, so just continuing on with our Mathematica notebook, let's go ahead and now compute the eigenvalues of CBV. Okay, so this was our matrix, so let's just go ahead and ask Mathematica to calculate the eigenvalues of this thing. And as you can kind of see, that appears to be not super pretty, but you know what's interesting? If we look at this as a list, and actually, tell you what, let's simplify this, because maybe that'll make this a little bit smaller. Well, it's a little bit smaller. What we're getting at, what's terribly interesting about this is, as you can imagine, the second and third eigenvalues are a little bit ugly here. But what's fascinating about this is that, look at this. One of the eigenvalues, it's just 1, right? The very first eigenvalue is just it's just unity, right? Doesn't matter what your Euler angles are, phi, theta, psi, they can be anything. It doesn't matter. One of the eigenvalues is just the number 1. So let's hop back to the whiteboard and think about what are the implications of that.
Okay, so this is really fascinating. So we saw that one of these eigenvalues, I don't know, let's call this lambda, it doesn't matter, let's call it lambda I. One of the eigenvalues of this thing is going to be 1, okay? Of this matrix, okay? So what's the definition of the eigenvalue eigenvector? If you remember, right, the definition of the eigenvalue slash eigenvector, right, for any matrix, it's just the matrix, well, I guess I don't want to call it A. Let's keep calling it CBV, because that's the matrix we're talking about, right? CBV, the matrix times the associated eigenvector, let's call it VI, is equal to lambda I VI, right? That's the definition of an eigenvalue and eigenvector, is it has this relationship here, right? Well, if you remember, what is this eigenvalue for this particular one? If I look at the eigenvector-eigenvalue pair associated with the eigenvalue of just 1, we end up with this, right? It's CBV times VI is equal to VI. Okay? What does this mean? If you remember, this is a rotation matrix, and this is the vector that the rotation matrix is operating on. So if you think about this long enough, what this says here is it says that this vector, if you pick this vector VI, this rotation matrix, after you rotate it, it does nothing to the vector, right? It is completely unchanged. So the vector VI is not rotated by the DCM CBV. right? So this is kind of an interesting statement here, right? It says that the rotation matrix doesn't actually rotate this vector. So the next question should probably be like, what kind of vector is unchanged by a rotation matrix, right? Now, to answer that question, let's go ahead and recall Rodrigues' rotation formula. Okay, so let's take a quick side note. And if you remember what Rodrigues' rotation formula, it said that if you had a given vector u, right? So this is a given vector. Okay, it could be any vector in space, and then you had some axis of rotation n, right? So here n is the axis of rotation. Okay? And what you ended up wanting to do was you wanted to rotate this vector u about this vector n through an angle mu. And Rodrigues had this as a left-handed rotation for whatever reason. Again, we discussed the details of this in the previous video on Rodrigues' rotation formula, but again, this is not going to matter here. The idea here is if you rotate u about n through a left-handed angle mu, you would end up with a new vector v, right? So here's the rotated vector. Okay, so again, what's going on here, I made a little prop earlier in the video, but just to refresh your memory, let's say that maybe this green pen is your axis of rotation n. The black pen here is this given vector u, and what I want to do is I want to rotate it through a left-handed rotation mu to end up at this new vector v here. Okay, so let's go ahead and first let's write out the Rodrigues rotation formula, right? It said that given this setup, it said that v is equal to 1 minus cosine of mu, right, times the inner product of u times the axis of rotation n times n plus cosine of mu times u minus sine of mu times n crossed u, right? That was the formula, okay? Now, here's what's fascinating. What if we choose the vector that you're rotating? Let's choose that to be, aligned with the axis of rotation. So it's some scalar, let's call it alpha times n here. So physically what this means here is the vector being rotated, maybe we should write this down, vector being, B-E-I-N-G, being rotated is aligned with the axis of rotation. Okay? So all we need to do now is plug in u is equal to alpha n into this expression. Okay, so let's quickly do this. Maybe I'll do one step and hopefully this is we'll see where this is going, right? So cosine of mu, this times the inner product of, what is this? This is alpha n dotted with n, right? Times n plus cosine of mu, and then here is, what is u here again? It's alpha times n minus sine of mu, sine of mu, close that parentheses, times n crossed with alpha n, right? Okay, so let's go ahead and do this. Okay. A couple things that we notice here. This cross product, right, this is going to go away because n is aligned with n. It's in the same direction, right? You cross two vectors in the same direction, it becomes a big fat zero. So this term is gone, right? Okay, so what do we end up with? So we end up with, let me see, this is 1 minus cosine of mu times dot product of, I guess we can pull the alpha out of this. It really wouldn't matter. So I guess we can write this here as alpha times n dotted with n times n plus cosine of mu times alpha n. Okay? Okay, now what we should have also recalled here is that n is a unit vector, so its magnitude is 1. maybe we should have, I forgot to put this up here. This axis of rotation, this n is a unit vector, right? Describing it. Okay? So what that means here is, what do we end up with? This term, right? This just becomes, it's basically, this is 1, right? Because it's a dot product of a vector, which is magnitude 1, times itself, which is magnitude 1. So this thing is a big fat 1, right? So we end up with 1 minus cosine of mu, this whole thing, times alpha times n, right? That's that thing, plus, here, this one, cosine of mu alpha times n, right? And, okay, so I think if you start distributing this out through, you see that this term, here's cosine mu alpha n, here's negative cosine mu alpha n, so this guy will get knocked out by this guy, right? So what do we end up with here? We end up with, this is just alpha n, right? Okay, and if you notice, what is alpha n? Alpha n is just u, right? So at the end of the day, we end up with this. What does this say here? What this says is that the vector, if you choose it to be aligned with the axis of rotation, it doesn't change, which makes perfectly good sense if you think about this. So let's maybe summarize this here. So if you rotate any vector about its axis of rotation, it is unchanged. Right? So that makes perfectly good sense, right? If it makes physical good sense, right? Because again, coming back to our picture, right? If you have some axis of rotation, right, which is this green pen, and you choose a vector, any vector that happens to be aligned with this axis, and then you just start rotating it through this angle mu. I mean, I don't care what mu is. You can rotate it through any angle. The overall vector doesn't change, right? It stays the same. Isn't that exactly what we were just talking about right over here with this eigenvector eigenvalue analysis? So what this is saying here is this eigenvector, right, you rotate it through the DCM by any angle, any psi, theta, phi, right, and it does not change, right? Therefore, doesn't that imply that this vector here, this eigenvector, has to be the axis of rotation of this Euler rotation sequence, right? So we end up here with basically that this eigenvector vi, right? This is the axis of rotation of the entire Euler sequence. And again, you probably want to normalize this just to, you can normalize it just to make a unit vector if you want, but otherwise, it doesn't matter if it's normalized or not. It basically defines the axis of rotation, right? So again, this vi here, this is the eigenvector associated with the unity eigenvalue in your direction cosine matrix, right? So this is pretty darn cool. This gives us a way to calculate that axis of rotation, which should take us from the vehicle carrying northeast down frame to the body frame. If we rotate about this single axis, we should be able to get there with just one rotation instead of 3 that we're using in our Euler sequence, right? So that's pretty cool. Why don't we go over and look at an example of this?
All right, so we switched over to Matlab again just because I think it's a little bit easier to do some of the plotting, but let's use that exact same example we were looking at earlier where we had a yaw angle of 70 degrees, a pitch angle of 130 degrees, and a bank angle of 25 degrees. So let's go ahead and, whoops, that should be compute, CBV. So let's compute the entire direction cosine matrix as we did earlier in Mathematica, right? It's just the product of these 3 Euler rotation sequences. And now what I want to do is let's get the eigenvectors and the eigenvalues of that matrix right here on line 56. Tell you what, let's take the semicolon off so that we can actually see the output to the screen. And I will put put a breakpoint right after it. Okay, so let's just run to that spot. Let me just scroll back up here. Okay, so we just executed line 56, and you see that here are the eigenvectors, and here are the eigenvalues, again, on the diagonals. Remember, what Matlab does is it sticks the eigenvalues here on the diagonal. So you see, here's an eigenvalue, and you see that's one of those weird ones in Mathematica where we saw it was kind of complicated, so it's imaginary in this case. Here's a second one, which is also imaginary. But look at this. As we saw earlier, it doesn't matter what the Euler angles are. One of these eigenvalues is guaranteed to be 1. And here it is. It turns out it's the third eigenvalue is what Matlab decided to return. So what we need is the third column of the eigenvector matrix, right? This column right here is going to be the eigenvector associated with the unity eigenvalue. So that's what I'm just doing here on these next 3 steps here is we see that the index of the identity for the unity eigenvalue is the third index, right? Index 3. So I'll just pull off that eigenvalue right here. That better be a 1, right? Lambda has to be 1, as you can see right here. And V, the vector that we're interested in, is again this third column here. So I'm taking all rows, the third column of the eigenvector matrix. So if I just go ahead and step through these, right now we have lambda, which is 1. Yep, and V, which is the eigenvector. So this is the axis of rotation that we just discussed on the whiteboard. So what I want to do now is, tell you what, let's go back and draw ourselves the vehicle carrying northeast down frame, and then the body frame that was obtained by rotating through these 3 angles, right? It was basically that Euler rotation sequence that we were looking at earlier in the lecture. So I'll just hit F5 so we can draw this picture, and let me just dock this figure. Okay, so again, this should look very similar, right? The red was the northeast down frame, the blue was the body frame, and earlier what we had done is we had done our 3 unique rotations by going about, or sorry, I shouldn't say unique, I should say 3 individual or separate, right? We first rotated about the Z, then we rotated about the Y, then we rotated about the X axis to get to the blue axis, right? That's how we got from the northeast down to the body frame. Now, what I want to do is let's plot this axis of rotation here, right? I think in Rodrigues' terminology, we called it the vector N, right? N is the axis of rotation. We are going to choose that to be the eigenvector that's associated with the unity eigenvalue. So if I go ahead and just plot that, that is this magenta line right here, right? So this magenta line is the axis of rotation. So what I want to do is basically I'm going to apply Rodrigues' rotation of a vector formula using this magenta line as the axis of rotation, and let's just go ahead and rotate the X northeast down, the Y northeast down, and the Z northeast down frame through an angle mu. So I'm just going to go ahead and let this run, and let's see what happens to this X, Y, and Z of the northeast down if I rotate them around this single axis of rotation here. So let's go ahead and just do that, and I'll let this run. Oops, sorry, I got to take off these breakpoints so this thing runs a little bit more smoothly. And there we go. So that's the green is we're rotating those, and we see eventually with the mu equal to here about 233.5 degrees. Look at this. We basically went from the body, the vehicle carrying northeast down frame to the body frame by just this single rotation about this magenta line, right? About that eigenvector. So this is pretty darn interesting. I think it's pretty helpful and very, I guess, interesting is maybe the right adjective, because it's neat to notice, but again, most of the time we are going to be using these 3 individual Euler angles of phi, theta, psi. But this just is used to illustrate that, you know what, there's more than one way to skin a cat, right? You could also get to the body frame through a single rotation about this single axis of rotation.
Okay, and maybe one final remark before we leave our discussion on Euler angles. Sometimes you may hear intrinsic versus extrinsic Euler angles. And all this is referring to is, in our sequence here of Euler angles, these are sometimes referred to as intrinsic Euler angles? What that means is that the Euler angles are defined relative to frames, but these intermediate frames rotate with respect to one another, right? We saw that. The one frame is not aligned with the original northeast down frame. The two frame is not aligned with the one frame, and the body frame is not aligned with the two frame, right? We have to go through this sequence of everything changing on one another in order to get to that. So this is what we just discussed, right? So this is phi, theta, psi, how we typically define it. Extrinsic could also be defined. This is sometimes referred to as if the Euler angles are defined relative to a reference frame which is fixed and doesn't move, okay? Now, the reason I bring this up is because our choice, or I guess it's the aerospace industry's choice, or whoever's choice, like the typical sequence that you'll see here, is using these intrinsic Euler angles. This is going to have some ramifications later on down the road where we want to relate how do Euler angles relate to, say, instantaneous, say, rates of change, say like the angular velocity vector of a vehicle, okay? So that sets the stage for our next discussion here on kinematic matrix relationships for rotation. And I hope you'll consider joining us at that discussion, because we're going to take this relationship that we just derived about using these intrinsic Euler angles and look at developing a sequence of equations that are going to allow us to relate rates of change of the body to rates of change of Euler angles, okay? So that's our next discussion. So with that being said, I think this is probably a great spot to leave it. I hope you enjoyed the discussion today, and if so, I also hope you'll consider subscribing to the channel. Surprisingly, if you just scroll a little ways down and click on that subscribe button, it really does help me continue making these videos. And with that being said, I hope to catch you at our next discussion, where we're going to be taking a look at kinematic relationships between rates of change of a vehicle and their rates of change of their Euler angles. So until we talk later, I'll see ya. Bye.